Hey guys, welcome to lecture number 2 in Calculus 1. So today we will continue our adventure in the with functions and graphs. And remember last time we talked about different type of functions. You have seen how their graphs look like. Also, we classified the functions. You have seen so a bunch of polynomial functions and other elementary functions as well, and also trigonometric functions. And now I would like to do something. So today I would like to veer to go a little bit further with the functions. And remember, I told you the last time that this lecture we will talk about the so-called inverse trigonometric functions. So let's get started. And also you'll see some other properties as well. So today's lecture will be inverse functions, right? Well, these inverse functions, and you'll see what do we mean by that. Well, I think you have seen probably. So let me just tell you what I'm going to do as a rule. I'll send you the materials in advance to look at them, to have an idea what I will be talking about in the next lecture. And then in the next lecture, you can ask the questions and so on. I think I sent you the video from last semester, right, as well. So these inverse functions, and you will see that they play a very important role especially when we would like to find the inverse of a function, but we will see what this is all about. So let's get started. And now, before I even go, let me recall something. As a rule, we would like to, last time we talked about the functions, right? And we said that a function is a rule that sends x to f of x, right? And we have seen a bunch of examples, as we have seen. Well, for example, if we have this function, let's take a simple one, 2x plus 3. You see, this number, an f, let's say, is defined on reals and real value. Well, as you can see, this number, by taking this real number x, right? This belongs to, okay, I'm going to write it like this. This will be sent to this another other real number, 2x plus 3. Again, this belongs to R. So this is also a real number. Anyway, maybe I should, let me erase this. Right? So this is what I mean. So you take this x and you send it to 2x plus 3. For example, if you take x equals 0, this will give you 2 times 0 plus 3, which is 3. So the number 0 is sent through my function f to the number 3, and so on. You can plug in -1. For example, if you have -1, you have 2 times -1 plus 3, which is 1. So the number -1 is sent to 1. So you have this kind of correspondence, right? So the correspondence is given by this guy here. So that's what we mean by when we say that a function is a rule, because it's a rule at the end of the day that sends x to f of x, right? But I'm sure, okay, I hope this is clear for everybody. Now, what we would like to do is to reverse this process. So we would like to send f of x back to x, if that's possible. So that's what we would like to do, right? All right, so how are we going to reverse this process? We will reverse this through what we call the inverse functions. So if we have something like x will be sent to f of x, so let me draw the picture here. X is sent to f of x through f, right? Let's write it like this. Then I would like to reverse this process somehow. So how should I send f of x, the value f of x, back to x? And this reverse, the reverse of this process is what we'll write this f to the -1 of x. And this is what we'll call, this is the inverse of f. So this will be the inverse of my function f, right? All right, so let's talk about. So an inverse function for f of x is a function f to the -1 of x, such that these two conditions are met. So you see, f inverse, that's how we're going to read this, of f of x is x, right, is the identity, and f of f inverse of x is the same, is the identity. In other words, instead of writing like this, since we learned last time about the composition of functions, this would be nothing else than just, okay, I'm going to write it here, f inverse composed with f of x, right, let me delete this, right, is x. So that's the condition that, in fact, let me write it here so that it's even clearer. This is equivalent with saying that is the same as f inverse composed with f of x is x, right? We have seen this last lecture. We said that the composition of two functions, f and g, f composed with g, f circ g, right? It's a circle there, a little circle. F composed with g is f of g of x. And this is exactly what happens here. So f inverse of f of x is x. Or you can say that f inverse composed with f is the identity. Also, this x we can call, you will also call it the identity function. And the same goes here, right? So you can say this guy here, f of f inverse of x is x. You can say that f composed with f inverse of x is x. In other words, if we want to combine these two, we say that an inverse of for a function f of x is a function f inverse. So let me just stay here. So we read this f inverse. By the way, the interpreter doesn't need to be in the waiting room. He can just put the code and that's it. Yeah, I saw the message. So I sent the email to the interpreter as well. So you can just click and let me see here. I see, Ashley, you have the dog. I like that.
Yeah, sorry, he decided to join.
No, it's fine. It's fine. It's fine. So don't. I mean, well, we read the rules, but I'm not the strictest possible. The only thing I will require is just to have the cameras on. That's so that I know that you're here in the lecture. But you can eat. You can. Yeah, I mean, you can bring dogs, cats, whatever. I don't mind. Anyway. I hope so the interpreter just, I wanna, is he here? Anyway, probably. All right, so let's get back to, so in other words, if you would like to, I wanna make myself clear, when you have f to that power -1 there, you read it as f inverse. That's the inverse. I hope my handwriting is clear. Let me write it again. So that's, let me write it with capital inverse, F inverse. That's how you're going to read it. All right. So this is F, the inverse of F. And if we would like to combine these two into only one, so we can say that F composed with F inverse of X is the same as F inverse composed with F of X, and it's X. So that's what you need to know. Right? So you see, either way you put it, on the left, on the right, it doesn't really matter. That's the rule for the inverse of a function to exist. So keep this in mind because we would like to use this definition. All right.
Oh, dude, also I realized from math homeworks, they're not due till March 17th.
Yeah, I already said at the
They
beginning.
just all do it one time.
Yeah, 3 of
I
them.
know. I was like, fuck yes. I was like, I don't have to stress about like every week having to turn in something.
By the way, somebody has his mic on. I know. I thought you were talking to me. Anyway, so make sure you put your mic off once you, so when you want to answer a question, you turn on your mic and immediately after I start speaking, turn off your mic because I might hear you might say some God knows what, and everything is recorded right now. You know, some crazy things happen. I can send you some links. There is this, anyway, somebody at my former institution when I was a PhD student, somebody was complaining about their love life and they forgot they're recorded, so everybody heard about it.
You should upload a bloopers reel to your YouTube channel.
All right, so this is the what's going on with the inverse functions. All right, now I want to make myself, you see, this is you. I want to make myself clear about something. This is the danger. F inverse is not the same as 1 over F. So when you say that find, when I'll give you an exercise and I'll tell you if like find F to the negative 1 of X, and you say like you're going to write 1 over F of X, that's wrong. So you're in the danger zone if you do that. So make sure you don't do it. So this is a big caution. F inverse of X is not the same as 1 over F of X. So please keep this in mind. All right, and now I would like to give you an example. So let's see, you see, how do we find, so the question is, let me write it here. So the big question is, how do we find the inverse of a function? Right? So that's the big question we would like to answer. So in other words, you will say, so all right, given a function f, is there a way for us to find f inverse, not 1 over f? So when you see, once again, when you see f to the negative 1 of x, you will immediately know that that's the inverse. It's not 1 over f. Otherwise, you will be asked to find 1 over f, but that's, all right. So look here. If f of x is 2x plus 1, then f inverse of x is x minus 1, everything over 2. You'll be like, oh, how did you find this? All right, there is a procedure to find the inverse of a function, and I will describe it. Well, let me tell you one thing, because I would like to say, again, I would like to emphasize again that you see, if f of x is 2x plus 1, then by some miracle, we'll see how. F inverse is x minus 1 over 2. But you see, clearly, f inverse is not the same as 1 over x, because if you compute 1 over f of x, for example, if you plug in x equals 7, 1 over f of 7, right? You see, f of 7 is 15, 1 over f of 7 is 1 over 15. But f inverse of 7, if you plug it in, you see you have 7 minus 1, everything over 2, that's 6 over 2, that's 3. As far as I'm concerned, if you look at these numbers here, you see they're not the same. So that's one more reason to think that f inverse is not the same as this. So so these two are not the same. Anyway, you can ask, how did you get that? So how did you get f inverse of x is x minus 1 over 2? Anyway, we'll get there. But first, let me start with a problem. Look here. F of x, I'll take f of x to be the simplest quadratic function. And let me just... You see the graph? The graph is a parabola, right? As you can see, the lowest point is here at the origin. This is 0, 0. Also, you see that, for example, f of 2 is the same as f of negative 2. So the question is, like I said at the beginning, so you see, x will send me to f of x, and now I'll have to go backwards. So how are we going to go to, well, we would like to try to go backwards from 4, and well, where should we go? Should we go to 2? Should we go to negative 2? That is the big question, right? Because clearly 2, okay, I'm going to write it here. 2 is sent to 4, right? Because f of 2 is 4. And clearly negative 2 is also sent to 4. Right? So the big question is, how are we going back? From 4, where should we go? To 2, to negative 2? And this is where the problem will start. And I'd like you to pay attention very carefully here. And because we would like to see that this will deal with what we will call injective or one-to-one functions, or we will also see surjective or onto functions. So we will define 2 classes of functions. And let's start with the first one, definition. A function f is one-to-one, or sometimes we call this injective. Let me write it here. So when you see the word injective, you will know that this is nothing else than just one-to-one. So by the way, I have a question. I see somebody taught twice. Taylor Henderson?
We're twins.
Oh, okay.
It's Taylor and Tyler.
Yeah, okay. Okay, mute your microphone on one of them. So, okay. Because you're not, the funny thing is that you're not at the same time. So sometimes the Taylor Henderson, probably from the laptop, is doing something, then probably from the phone is doing something. I'm gonna be like, it's the same person, but anyway, that's what happens with Zoom. Like I said, a function f is one-to-one if this condition happens. Look at it here. If f of x1, so given 2 points, such that f of x1 is the same as f of x2, this will imply that x1 equals x2. This is a very important condition. Keep this in mind. Now, well, if I'm asking, well, this is the definition of one-to-one. And if I ask you for an example, what do you think? For example, are the linear functions one-to-one? For example, if we take that function at the beginning, f of x equals 2x plus 3. F is defined on R and real value. The question is F 1-to-1? What do you think? Based on this definition. And after that, we'll go back to the function above, to x squared. But I would like you to think of this. So what do you think? Do you think this is 1-to-1 or not? So by just looking at the definition. Somebody says yes. Well, everybody agrees with that?
I don't think it would be though.
Why would you say that?
Well, because I feel like the parabola would be, because they both have like.
Wait. I'm talking about f of x is 2x plus 3 here.
Right. I'm just like, I don't really know how to describe it. I just feel like, because if you put in two different like values, like, so like, you know, -2 or something and 2, I don't know if it would work.
Actually, surprisingly, your intuition is not correct here, but your intuition will work on the example above, and we will see that on this problem. You see, anyway, we'll get back to f of x equals x squared, but first, let's look here. And in fact, before I even go, let me just say even more, and then we'll see this example in detail. So what does this mean? This means that every y is the image of a unique x. This is important. So that's what the injectivity or 1-to-1 stands for. So it's a unique x. Okay, maybe we should do it like this. This is x is unique. This is important. Right? So in other words, in our case, if we have x1 and x2 such that f of x1 equals f of x2, but f of x1 is 2x1 plus 3, and f of x2 is 2x2 plus 3. Oh, plus 3. Oh, sorry about that. I hope it's not COVID again. Well, I must have some immunity by now. Well, as you can see, if we take x1 and x2 such that f of x1 equals f of x2, this will clearly imply, since f of x is 2x plus 3 from here, this will be equivalent with x1 equals x2. I think it's obvious for everybody, I hope. So this will imply that f is 1-to-1. Right?
Wait, so does 1-to-1 only apply when the equation is the same, or does the x have to stay the same? Like if they come out, so is 1-to-1 basically just saying the equations are the like same for both x1 and x2?
2, and then yes, when the equations are the same, this will imply that the variables are the same. Yeah.
Okay, gotcha.
Or in other words, if you, for example, anyway, we'll see. Now let me go back to, so you see this function is 1-to-1. But now, what do you think about this function if I want to go back to it? Do you think f of x, and let me just be specific here because it's defined on the entire real line.
Well, wouldn't it still be 1-to-1 because x is squared, so it can be a negative or a positive 2 to get 4?
Yeah, but you see, you have something here. Let's say you have, look, f of 2, just by look at this example, f of 2 is the same as f of negative 2, right? So if
Yeah.
f is, right, it's because they're both of them are 4, right? But, ouch, but what does it, what would, if f was 1-to-1, this will imply what?
The both
Is negative 2, which
Are-
is false.
different.
You see?
Okay, I got you.
So if f is 1-to-1, then I'll have 2 equals negative 2, which doesn't happen. You see? So for x1 and x2, which in our case x1 is 2, x2 is negative 2, we have such that f of x1 equals f of x2. Look at them, look at the definition here, right? It will imply x1 equals x2, but in our case it doesn't imply that. So this means that my function, the quadratic function, is not quite injective on the entire real line. So you see, every linear function, so a degree 1 is 1-to-1, but if you, and defined on the real line, but if you go on just to the simplest quadratic function, right, to the parabola, f of x equals x squared, and if you would like to define it in the same way on the entire real line, well, bad luck, is not 1-to-1. So I'd like to pay attention here, and that's why it's good that we draw the graph, because there is a theorem which says that, and we'll, by looking at this graph, look at this graph. What can you tell me about by just looking at this graph? So there is another reason why why this function is not 1-to-1 on the entire real line. And first, let's look at the graph. What can you tell me by just looking at the graph, at the parabola? What can you tell me about the function? So the graph is decreasing, right, from negative infinity to 0, and then it starts increasing again, correct? All right, and there is this theorem which says that any monotonic, whatever means increasing or decreasing function, is 1-to-1, but not the other way around. So if I restrict this function only to this side, only to, let's say, this part here, so starting from 0 all the way to infinity, so my function probably will be 1-to-1, but only on this part here. Or maybe if I'm restricting to the negative part, the same thing will happen, right? So this is important, but by combining the two is not a 1-to-1. Is it clear what I'm saying for everybody? Okay, that's good. All right. So that was the definition. Keep in mind that we're gonna need this in order to find the inverse. So we need to check if, in order to find an inverse, we need to check that f is injective, or 1-to-1, but we'll get there. And now, let me tell you something graphically how you will see that a function f is 1-to-1. And this is what we call the horizontal line test. And again, as you can see, I have the graph of the parabola. And this will give you another reason why a function will give you a way to test if a function is 1-to-1 or not. So the horizontal line test reads as follows. A function is 1-to-1 if and only if, so it goes both ways, its graph intersects the horizontal lines no more than once. I repeat that. So a function is one-to-one if and only if, not just if, it's if and only if. So it goes from left to right and right to left. Its graph intersects the horizontal lines no more than once. So let's just take some horizontal lines here. For example, if I take a horizontal line here, and this, how many times does the graph intersect this horizontal line? Well, that line is not quite horizontal. I mean, I'm not the most talented guy in drawing that you will ever meet. Even this one is not quite horizontal, but anyway, you will imagine. So let me write here, horizontal line. So how many times does this horizontal line intersect the graph of f? Once, you see here. Let me take another horizontal line. Well, you know, I can take even this, the x-axis to be the horizontal line. Ooh, you see here. How many times intersects? Well, again, here. Or you can take another horizontal line. Let me take one here. It doesn't have to be a -2, but you see the graph intersects again once here. So what can you tell me about this function? What do you think this function is like? This function on the left. Is it one-to-one or not?
No.
Why is it not? How many times does the horizontal line intersect the graph?
Twice.
Right? So, well, I'm asking about a horizontal line. Once, right? So, not, of course, if I'm taking 10 horizontal lines, they will intersect the graph, but it doesn't intersect not more than once. But what if I do the same thing here? Let me take another horizontal line. For example, we look, I'm going to take 1-to-1 here. How many times does this horizontal line intersect the graph?
Twice.
Twice. You see, you have 2 points here and here. And this is the graph of, let me say it again, of y equals x squared. So this is the problem. So this is another reason why the function f of x equals x squared is not one-to-one, because if you take a horizontal line, it will intersect the graph in at least 2 points. And you can take another one if you want. For example, you can take one here. You look, intersects in 2 points again. So you have plenty of reasons to believe that f of x equals x squared is not one-to-one. So it intersects in at least 2 points. So it's more than just once. So that's the horizontal line test. And now let me say a few words about graphing inverses, graphing the inverse of a function. And you'll see something if you look at these. If you look at these two graphs, can you see something? This guy here, let me say, y equals x, and the same goes here, y equals x. So this is what we call the first bisector, right? It keeps going. That's exactly what I didn't want to. Okay, sorry about that. All right. So by just looking at these two graphs, what can you tell me about them? look very, very carefully. So try to interpret them. And can you tell me, in fact, I'll be more specific with the question, how do these two graphs look like with respect to that line, y equals x?
Flipped.
Say that again?
They're flipped along
They're
the
B.
Reflection on y equal to x.
So they're kind of symmetric, right? They're reflected with respect to the line y equals x, right? So they're quite asymmetric. So that's what you need to know by graphing the inverse functions. When you graph them, they're symmetric with respect to y equals x with the first bisector. You see, they're very symmetric. Just look at them. They're basically flipped. They're symmetric with respect to. So that's what you need to know about graphing inverse functions. Keep this in mind. They are symmetric with respect to the first bisector. So let's write that. So they are symmetric with respect to the line y equals x. So that's what you need to know. And this picture, these two pictures show this clearly. This is shown, it's pretty obvious from these two pictures. Okay. And now, well, we've seen at the beginning, and I didn't tell you exactly how to compute. Let's see, how do we compute an inverse of a function? So the example is the following. In fact, I'll just show you. So what we're going to do is the following. When we would like to find the inverse, we're gonna set up f of, so in this case, we have this function. So let's say that f is defined on reals, and it's a real valued function. So in this case, we have that f of x is 2x cubed plus 5. So we'd like to find f inverse. So first we set up this equation. So you set up y equals f of x, right? So let me write here y equals f of x, or maybe I should write it f of x equals y. Which means that in our case, y equals, this is a cube here, 2x cubed plus 5. And now you're going to solve this for x. And solve for x. And once you solve this for x, so you're going to take 5 on the left-hand side. So this would be 2x cubed equals y minus 5. So in other words, this will give us y minus 5, everything over 2 equals x cubed, right? And now you're going to take the cube root. So you're going to find that x is this guy. So we solve it for x. Look here. Right? And now, once you do this, you identify that x by f inverse. So this will give us that f inverse of x is nothing else than just cube root of x minus 5 everything over 2. Right? So that's the procedure. Once again, what you're going to do, you're going to set up f of x equals y. So you're going to write the x in terms of y, but you will solve this equation, f of x equals y for x. And once you do that, that x will become f inverse, and that's it. For example, let me go back to our initial example. I want to go back to, is it clear for everybody, the procedure? Well, let me go back a bit. To this here. Because we said that if f of x equals 2x plus 1, then f inverse of x is x minus 1 over everything over 2, but we haven't proved this. So and here in this case, if you look at our function, so if we would like to show that the inverse is this, so let's write it somewhere here. So f of x equals y will be equivalent with 2x plus 1 equals y. So now we're going to solve it for x. So from here, this will be equivalent with 2x equals y minus 1, or equivalent with, if you want to say, x equals y minus 1 everything over 2. So that y will become x, and that x will become f of f inverse. And then once you have this, you can go back in here, and you'll have this. Right? It's the same procedure. It's clear now for everybody, I hope, right? Any questions about this procedure of finding the inverse? Well, if there is none, no questions. Is everything clear for everybody? All right. All right, that's great. So once again, you also have this example. All right. Now I would like to talk about something, because you'll see why this notion of inverse function is useful. And I would like to veer towards the inverse trigonometric functions. And I will explain the philosophy a bit. So look at this picture. You see, if you look closely, notice that the trigonometric functions, right? Whatever you want to take them, take any of them. Like if you want to take like sine, cosine, tangent, cotangent, it's very important to look at their domain of definition. And not just that, because these functions are a little bit more complicated, right? Sine, cosine. But even if when you looked at x, at f of x equals x squared, you've seen that that function is not one-to-one. If we define it on the entire real line. In other words, you can expect the same thing to happen for the trigonometric functions. So if you define sine on the entire real line, whatever, you will see that it is not quite, you cannot quite find the inverse. But if you restrict it to some domain, just like we did for x equals x, for f of x equals x squared, maybe this you will prove that is one-to-one, and therefore you can find the inverse. Right. So what I would like to say is that clearly that the trigonometric functions are definitely not one-to-one. But if we cut back their domains, so, and like I said, if we restrict them to some smaller domain, maybe they will be. And we will see how this will happen. So keep this in mind. This is very important. So once again, the restricted functions will be. So keep this word in mind, restricted. Right? just like I said, not only in the case of trigonometric functions, but also in the case of f of x equals x squared. If you restrict it to the positive side, it will be 1-to-1. Or if you restrict it separately to the negative side, it will be 1-to-1. But if you want to glue both of them and you say like, okay, I want to take both the negative and the positive side and put them together, it won't be. As we have seen, if you take the one number -2 and the number 2, f of -2 is the same as f of 2. They're both 4. So this is for f of x equals x squared. But 2 and -2 are not the same. So therefore, the function is not 1-to-1. So there is no way you will find the inverse of f of x equals x squared on the entire real line. All right. Well, what about the inverse trigonometric functions? The trigonometric functions take an angle and give you back a number, right? That's what, so, right? If you take, for example, you take x and you will give sine of x, right? You take a number, sine of x, you take an angle, sorry, take whatever, pi over 4, pi over 6, whatever, and it will give you back a number, right? I would like to tell you that I've done this. I've talked about the values of trigonometric functions in one of my videos, and also you'll see it in the notes as well. So make sure you know the values. I will not insist on them here. There is already a length video of about it. And now the funny thing, well, it's not that funny, but the real thing is that the inverse trigonometric functions will take a number and give you back an angle. So in other words, if I want to go back from here to here, this will be through this function, what we call sine inverse of x. Or sometimes it's denoted by arc sine of x. Right? I have a question. Is the interpreter here? I don't see him or her. There are two of them. Anyway.
Does that say arc sine x?
Yes, arc sine x. Okay, I'll write it here. Arc sine of x. Or sine to the sine inverse. So in other words, let me write it again. If I want to go back from sine of x to x, I'll do it through sine inverse or arc sine of x. Right? So that's what we're going to do. So once again, the trigonometric functions will take an angle and give you back a number, but the inverse trigonometric function will take a number and give you back an angle. That's a pretty nice procedure. So that's why you will see this is another example why this inverse trigonometric functions are useful. And now let's do a bunch of examples in the remaining time. Probably we'll finish up earlier today as well. What if I want to find cosine inverse of square root of 3/2? So this is nothing other than just arc cosine of square root of 3/2. What is this? Well, like I said, the inverse, so this is the inverse trigonometric function, the inverse trigonometric function of cosine. So it will take you a number and give you back an angle. So this guy here should be an angle. You have to think the function of which angle will correspond to the number square root of 3/2. Do you remember cosine of what? So in other words, cosine of what? I'm going to write here, what angle question mark, will be equal to square root of 3 over 2.
60.
60, right? Well, yeah, it will be pi over 6. No, 30, sorry. Yeah, pi over 6, correct. That's for sine. But the way we're going to do it, look at the picture. This will correspond to a right angle triangle. You see the distance here is square root of, well, you don't even need this, but honestly. But you can also say, you can set up a right angle triangle. You see, this is a right angle triangle. The hypotenuse, right, because cosine of an angle, right, of this angle, so of this angle, right, so this is our angle theta, let's say. So cosine of theta is square root of 3, so it is, yes, exactly, it is the adjacent leg over the hypotenuse, so it's square root of 3 over 2. So theta, it will be pi over 6. So you can see it like this, or you can remember the values. In any case, you have to remember them, right? So that's exactly how we're going to do. So if cosine of theta is square root of 3 over 2, now you can say that cosine inverse of square root of 3 over 2 will be theta, the number theta, which in our case is pi over 6. Yeah, right? Is it clear for everybody? All right. So that's the one way to go. Well, but this is the simple case. We'll see something a little bit more complicated. You see, and the complicated stuff is the following. Well, before I even go and talk about the complicated stuff, I want to make myself clear a bit before we go. I want to go back a bit. In fact, I'm going to ask you something. Can you tell me what is, let's say, cosine inverse of x? Can you tell me?
Would it be x?
Exactly. So like Kyle says, this is x, right? Remember at the very first definition, let me go back.
All students.
Look here. What did we say about the inverse functions? We said that an inverse of a function for f of x is a function f,
Okay.
right? So in our case, if you take cosine and cosine inverse, either way you compose them on the left, on the right, it has to give you the identity. You see, look at this here. That's why I insisted at the very beginning on this. Right, and now let me go back. You see, I have here cosine of cosine inverse is x, but also this is, if you write cosine inverse of cosine of x, this will also will give us x, right?
Yeah, because you have,
Keep that in mind. So when you compose a function, the trigonometric function, with its inverse, right, it will give you the identity. So keep that in mind, no matter the function. All right, and now here we go. This is a little bit more of a complicated example. You see, you have the tangent of the cosine inverse of x over 4. So look at it and try to think about it for a second before we discuss it. How would you approach such a problem? Well, you have something there, the tangent. So what is the tangent function? So tan of x is, if you remember, is sine of x over cosine of x, right? So you can write this as sine of cosine inverse of x over 4, everything over sine of, everything over cosine of cosine inverse of x over 4. Cosine of cosine inverse of x over 4, it's clear. We know it's x over 4, but we also have the sine. So what should we do? See, that's a little bit tricky. All right, let's see. Let's draw the triangle again. So that's why I would like to use this method, because it's important. And the way we're going to do is the following. You see, you have here x over 4. So this guy x over 4 has to come from some kind of a right angle triangle in which x will be the adjacent leg, or maybe it's the opposite. You don't know that yet. But since you have to deal with the cosine inverse, so maybe you'll think that the cosine of theta. So let me just, this is the angle theta. This is the right angle here. Since you deal with cosine inverse of x over 4, so maybe you'll think of cosine of theta as the adjacent leg over the hypotenuse and in our case, it is nothing other than just 4 over x. Also, on the other hand, let me tell you one thing. Also, by Pythagoras, so our good old friend Pythagoras, by Pythagoras theorem, what do we get? We have that 4 squared
plus x squared
equals this thing here, right? The second leg squared. Let's call it the opposite leg squared.
Mhm.
So the opposite leg will be nothing else than just
16 minus x squared.
Wait. I wrote it a little bit wrong here. Look what it's here is negative. So it's 4 minus here, not plus. 4 squared because it's the hypotenuse, right? But that's the Pythagoras.
Huh? Yeah. Maybe.
Right? It was a mistake. Remember, the sum of the squares of the legs will give you this the square of the hypotenuse. By the way, I remember. Did you see this meme with the social distancing at the restaurant? So there are 4 guys. Do you know the meme? So you know, with the COVID and stuff, there's putting all this. Posters, whatever they're called, try to social distancing, social distance. So they put something like this. So where should I write it? Okay, let me write it here. So the first person is here, says 6 feet. The second person is here. Then the third person is, you see here, 6 feet. The fourth person is here, again, 6 feet. But also they say that from here to here is again 6 feet. Did you see that? You haven't seen that? So basically, Pythagoras probably, that was the second time when Pythagoras died.
It's funny.
So yeah, it's 6 feet on the diagonal, right? This is the hypotenuse, so it shouldn't be that. So 6 feet, 6 feet, 6 feet. Poor guy. Anyway, so that was I will send you the picture. All right, so by Pythagoras we have this. So therefore, you can write a tangent. So what is the tangent? Is by just looking at this. So you know that the second leg, the opposite leg is this, right?
Oh, ka, toa. Opposite of
right? So this is the opposite leg, is square root of 16 minus x squared. So now it's, if you look at the tangent of this, is nothing else, what? Is the opposite leg over the adjacent leg, which is this. This is the opposite leg over the adjacent leg. Adjacent leg, anyway, whatever, right? So that's what this guy is. Another example is we would like to simplify a little bit tricky now. Sine of 2 arctangent inverse, tangent inverse of 3 over x. Well, here we would like to use something. Let me recall this trigonometric identity, which says that sine of 2 theta is 2 sine theta cosine theta. So by doing the same thing, right? By just doing the same thing. So sine of 2, the tangent inverse of 3 over x is nothing else than 2 sine of tangent inverse of 3 over x times cosine of the same thing. And now by just doing the same procedure, so this guy will be here, this guy is this guy, and this guy here will be this guy. By doing the same thing, so you draw the triangle, the right angle triangle, and you will see that in our case, so 3 over x, and you will like tangent. So you will have, since you want tangent is the opposite leg over the adjacent leg, right? So this is your angle theta, let's say. Look at here, right? And now you can find by Pythagoras. So by Pythagoras, you will find this guy here. You'll find the hypotenuse, right? And then you just do the same things. And at the end, it will give you something like this. Well, anyway, I'm a little bit rushing through this. Is it clear? Anyway, I was gonna leave the details to you yeah. So probably he waited on my, anyway, I'll check it. By the way, make sure I clearly specify which Zoom is for lecture, which one is for my office hours. So please read the emails correctly. But anyway, so that's the result. And I think I'm gonna stop here. Thank you very much. Let me stop the recording. So, well, I would like to say one thing. So this sums up the lecture for the first chapter, more or less. Next week, we will move to something more exciting, I would say. We will deal with limits of functions, then we'll talk about continuity and so on. So you'll see more qualitative properties of functions. All right, thank you very much. Let me stop the recording.